This video shows how to find the null space of a matrix. So what is the null space of the matrix? The null space of the matrix A, size n by n, is a subspace of the vector space Rn and is defined by the set of vectors x in Rn such that these vectors satisfy this homogeneous system Ax equals 0. Let's consider a matrix n by n in the vector space Rn by n, and the vector space Rn where the null space of this matrix A belongs to. So if you multiply this matrix A to any of the vectors in this null space, you help transform this matrix A to a vector 0 in vector space Rm. Let's look at an example. If you want to find the null space of this matrix A, then again, the null space of a matrix is the solution set of the homogeneous system Ax equals 0. So let's consider the system Ax equals 0. So in order to solve for this system, remember you want to translate this system into an arithmetic matrix, and then you're going to reduce this arithmetic matrix to its reduced row echelon form, which is this matrix. And then from this matrix you can try to solve for the system using leading variables and free variable. So observe that you see that there's two pivot positions on the first and second columns. There's no pivot positions on the third column. That means x3 is a free variable and x1 and x2 are the two leading variables. So since x3 is free, it can be any values in R, then you want to set x3 equals alpha or beta or any of the letters that you want to use. You just want to replace x3 by an arbitrary values, where alpha can be any values in R. And if you look at the reduced row echelon form here, you can see that x2 minus x3 equals 0. Thus, x2 equals x3, and since x3 equals alpha, then x2 also equals to alpha. Similarly, you can look at the first row of this matrix here. You know that x1 minus x3 equals 0, thus x1 equals x3. Since x3 equals alpha, then x1 also equals to alpha. Combine all of these variables together, you find your solutions x equals vectors alpha, alpha, and alpha. And since alpha is just a constant, an arbitrary constant, and it's a common factors of these three values, then you can factor alpha out. So then x gonna be equals alpha times to the vector 1, 1, 1, where alpha is in R, any values in R. So this is the solutions for the system Ax equals 0. By the definitions, it is also the null space of A. So the null space is a set of vectors alpha times the vector 1, 1, 1, and alpha is in R. Okay. So maybe we want to find a different way to describe this null space of A. In this case, we can use a span of a vector. So the span of the vector is a subspace that contains all the linear combinations. So if you look at the span of vectors 1, 1, 1, it is a subspace in R3 that contains all the linear combination of 1, 1, 1. And then we look at this form here, the form of these vectors in the null space. All the vectors can be described using alpha times 1, 1, 1, and alpha can be any values in R. That means alpha 1, 1, 1 here is actually contains all the possible linear combinations of the vectors 1, 1, 1. So we can rewrite the null space of A as the span of the vector 1, 1, 1 in R3. How can we visualize this null space in terms of span of vectors? We consider R3 as a three-dimensional space of x1, x2, x3. Okay. And we draw the vector 1, 1, 1, and then the span of 1, 1, 1 actually is just a line that goes through these vectors in R3. So you can imagine that in a linear combinations of 1, 1, 1, it's just a scalar of this vector. So that's why all the linear combinations of this vector 1, 1, 1 should contain in this line. A line that goes through these vectors 1, 1, 1 in R3. And this is just a line in R3.